Okay, thank you. So today is the last of these four lectures about lean, and we're going to talk about artificial intelligence applied to mathematics and specifically to mathematical formalization. Um, so let's start with a problem that maybe if you follow the tutorial, you may or may not have perceived, which is the fact that when we formalize stuff, mathematical stuff, we usually take more time for the formalization than we would have taken for just writing the mathematics down on paper or using LaTeX. And this thing was noticed already some decades ago, and some people give it a name, which is the de Bruijn factor. Now, specifically, the de Bruijn factor quantifies how much formal proof is longer than its informal counterpart. In particular, in this paper from the year 2000, the de Bruijn factor was computed using the size of the file of the informal proof in bytes and the size of the formal proof in bytes. And we have two different variations of these de Bruijn factor. The first one is called the apparent de Bruijn factor. That is, we just compare the sizes of the uncompressed files. So we just write them down and see how big they are. And the intrinsic de Bruijn factor, which is, okay, maybe we try to factor out like multiple spaces or longer names by compressing the files. And again, looking at the ratio. Now, of course, this is a very vague concept because we could make the proof shorter, both formally and informally, by compressing. Maybe informally, we can just skip some passages, or on the contrary, we could explain some things more in detail. And also in the formal proof, we mentioned yesterday during the tutorial that you can do what's called golfing, which means we try to make the proof as short as possible. So these factors can be gained a bit, but it still can give us like roughly an idea of how much more difficult it is to formalize things than it is to just write them down in full. Another definition that was given is the de Bruijn threshold, which originally was said to be the critical value of this de Bruijn factor, under which it becomes feasible to do serious mathematics with formal provers. But actually, I think this threshold has already been surpassed in some way, because we already have some examples of serious mathematics done with theorem provers. Maybe something that can be more interesting to look at is when this factor gets small enough that it's faster, or it's in some ways more efficient to do mathematics with proof assistance than without proof assistance. And of course, we're still not at that point, at least for general mathematics, even though there's like specific examples like the equational theories project, where in fact it was more efficient to use a theorem prover because it made things possible that wouldn't have been possible otherwise. But for general mathematics, we still have to get this factor down. Now, I'm not giving you a precise number for how much, what the de Bruijn factor is today. There have been some estimates for past systems, but they vary a lot depending on the specific style of the writer, both the formal and informal writer. It can go from around 4, so it's 4 times bigger a formal proof than a formal one, up to 20 times. So it really depends. But the real change would probably happen if we get this factor close to 1 or even under 1, because it's in some sense it's possible to even be for formalization to even be faster if we automate enough things. Now, to get this factor down, though, what we want to do is we want to make it easier to formalize things. So we want the theorem prover to do more work for us, because the total amount of work will ultimately be the same with the formal prover, because we cannot skip steps. We still have to put everything every detail of the proof down. But if we can make the theorem prover do many of the tedious details itself, then we can avoid doing them ourselves, and we can focus on the more high-level details of the mathematics. So what we'd like is, as I said, an easier way to formalize things. We would like formalization to be easier. And what can we do to make formalization easier? So what are the pathways that can lead to an easier formalization? Well, two things we can do is, well, we could have better infrastructure. For example, we could have better elaborators, better software to handle maybe the installation of Lean, or all the technical problems that are around. And this is currently being handled by the Lean FRO, the Focused Research Organization. And it's progressing over time. So tools are getting better over time. But another thing we would like to do is to have powerful automation. So to have, as I said before, the software doing actual mathematical steps for us. And how can we achieve better automation? Of course, you could do better tactics, for example, so deterministic automation. And this is also being done in part by the Lean FRO and in part by external contributors from the community. But the real tool that you can use to really make some mathematical progress that is non-trivial automatically are AI systems. So in the last few years, we've been witnessing the generative AI being born and being more and more powerful the more time passes. So we can hope that generative AI could do some of the work for us, or in the maybe not so near future, even all the work for us. We can hope that it automatically formalizes a full paper, or maybe even a new theory to develop new mathematics itself. Okay, great. So we have a tool that kind of works, but currently the AI models that we use are not so good at doing actual mathematics and formal mathematics, because they often have hallucinations, for example. They do not scale very well for like longer projects and longer theories. They maybe can do some simple steps and they're getting better. But the real thing that can help AI get better, at least from what we've seen until now in AI development, is having better data and more data. So to train an AI to do formal mathematics, we would like to have a lot of formal mathematics to train it on. So we need bigger libraries. Lean is, of course, already has already a good size, but it's nothing compared to the sizes of documents that are used to train large language models, because they're in the realm of the trillions of tokens. While, as we've seen, MATLAB has currently on the order of hundreds of thousands of theorems, so maybe millions of tokens, but definitely not trillions. So how can we get better libraries and bigger libraries and more formalized math? Well, this time we can actually close the cycle in some way, because if formalization gets easier, then we will have more data, because the people who are already formalizing stuff will be more efficient at doing so the libraries will grow faster. And another way we can grow the libraries faster is if we involve more mathematicians. So, of course, they will formalize more mathematics. And again, we have another cycle here that is in the way of formation, because if we want more mathematicians involved, we also need to have better tools, easier tools to use. And again, we can rely on this we can hope a positive feedback loop. And just to close this cycle here, actually more formalized mathematics also means easier formalization, because we do not need to start from scratch from mathematical foundations if we already have a well-developed theory. So if we have already a well-developed theory, like in the field of algebraic geometry, then we can hope to start formalizing an algebraic geometry paper without like years of works. So today we're going to focus a bit on this part of this graph. So how do we get better AI? How can AI help us get better automation and formalization? So what can we do? What can we make an artificial intelligence model do related to mathematics, and in particular formal mathematics? Well, the first thing that comes to mind is I just ask the model, please prove me something. Please prove me this theorem. I provide you the statements, and I ask you, okay, give me a proof of this statement, which let's hope it's maybe correct and complete and not buggy. But that's not all. We can ask the AI model to do other things that can be maybe easier, but still useful. For example, we can ask it to do autoformalization, which means we start from a paper which is completely informal, and we ask the AI to translate it into a formal language, which is currently the work that many people in the Lean community are doing manually. Another thing we can ask it to do is, okay, I'm stuck maybe at some point of a formal proof. I'm trying to prove something. Can you help me by suggesting me some lemmas that can be useful in this situation? And this is called premise selection. So the AI understands what's the problem at hand and tries to suggest lemmas that maybe are not all correct, maybe they're not all useful, but it suggests 10 lemmas, and maybe one will be the lemma that I need in this situation. Another thing that we've actually already seen is auto-informalization. This can be also done without AI models. In fact, as I told you a few lectures ago, Lean Informal is already under development, and as far as I know, is not based on AI models. But still, AI models can be used to improve auto-formalization and to maybe diversify and maybe make auto-informalization also in different languages. And more human-friendly than what a deterministic system could do. We could hope that someday AI could also be conjecturing theorems, maybe building up whole theories by itself. And then there's other specific tasks that we can make an AI do related to mathematics, and in some weak sense also to formal mathematics, which are domain-specific tasks. And we're actually going to start from these kinds of tasks and then build up to more like general theorem proving later. So we're going to start with a tool that's called Pattern Boost. That is a domain-specific tool. This is a general method. I mean, it's domain-specific, but it can still apply to different domains. Because it's a method to find mathematical objects with extreme properties in some sense. By leveraging artificial intelligence and the generation capabilities, in particular of transformers. So the idea is we try to look for candidates by alternating some deterministic, which we call local, so algorithmic steps, with some more like AI-driven, which we call global steps. So basically, we make the AI produce a lot of things. We kind of guide it to the things that we like the most, and then we hope that it will improve in producing the specific things that we like the most. And let's see specifically how it works on an example, which is producing graphs which have as many edges as possible, but without having triangles inside. Okay, so that's a task that we can try to do by hand, or we can try to prove maybe theorems that say, okay, this specific graph is maximal with respect to this property. But maybe before we prove the theorem, it can be useful to have a lot of examples of extreme graphs in this sense. So what is done in this situation is first we define what's called a score function, because this task that's well, it's not a continuous task. Okay, we're just asking, okay, I want a big graph with no triangles. An easier thing to do maybe to try to minimize the number of triangles instead of forcing them to be zero, because then the model can build up a graph with less and less triangles. So we define the score of some graph as the number of edges minus twice the number of triangles. So to improve the score, it can either make more edges or remove triangles. Then we try to generate a data set. You know, in artificial intelligence, it's useful to have data sets to train your models. And in this case, well, we can generate a data set algorithm. Maybe the graphs that are generated will not be good graphs with respect to our score, but we can start from there at least. And this is, for example, the distribution of the graphs. This is the score. These are the graphs produced by some random algorithmic program. And they have, there's a few which have a decent score. And in this case, the best possible score is 100 for this the specific number of nodes. Then we can just select the best candidates from this distribution to train a model from scratch. And we train this model to produce more of these candidates. We can use a transformer architecture because it's very useful to use a transformer when you have some data which can be represented as text. And in the case of graphs, we can represent graphs as text using their adjacency matrix made of zeros and one, and we just take the matrix and we linearize it into a list of zeros and ones. And we try to make the transformer produce new graphs from this. So we only select this. This is just the rightmost part of the distribution we saw before. We train the model on these. And then what we do is we make the transformer produce new graphs. And at first it will produce a distribution like this. So it's not as far as the distribution we saw before, but it already has some more extreme examples, even a couple which are near 100. Then what we do is we make this graph. We try to make these graphs a little bit better through algorithmic methods. For example, we try to remove edges to break up triangles, and we try to randomly put new edges in as long as we can without making new triangles. So we basically try to shift the distribution on the right. And then we train again the models. We fine-tune it on the best graphs that we found, and we repeat the process many times. And the distribution goes like this. So after a few cycles of this, we have a model that can consistently generate very extreme graphs with very high probability. And then we can use those graphs either to maybe find a counterexample. Maybe we're looking for a specific graph, and we think that for some reason, if the graph has a high score, it has a good probability of being a counterexample to a problem. Or maybe we're just trying to understand the problem better, so we want to see many examples for getting the idea of this. And this can be applied to many different problems, especially combinatorial ones. And we already see now in this model the combination of artificial intelligence and mathematics. But in this case, it's a very, very specific domain of mathematics. And since it's so specific, we basically do not even need a language to talk about it. I mean, we have a language which is the string of zeros and ones that describe the graph, but it's a very, very limited language. It doesn't allow us to express general things at all. What we want to do with more general mathematics is to have a more expressive language. So let's see an example that's a bit more expressive in this sense, which is alpha geometry. You may have heard about alpha geometry. This is an AI model from Google DeepMind, which uses AI to solve planar geometry problems, so Euclidean geometry problems of the kind that you may see, for example, at the mathematical Olympiads in the geometry section. Now, what alpha geometry does is it actually translates a geometric problem in its own specific language. So they developed a language which can talk about geometric objects in 2 dimensions. So it's an expressive language in some sense, definitely more expressive than the adjacency matrix of the graphs, because it can talk about different properties of mathematical objects, of the geometric objects. But still, it's still only contained into the planar geometry world. Now, how this system works is it takes the problem gets converted into this domain-specific language. It's just the graph problem. And then what it does is again, you have the intersection between some algorithmic steps and some AI-driven steps, because there's what's called a symbolic deduction engine, which basically takes all the facts that are true for this problem and deduces everything that it can. It has a fixed set of theorems inside, which it can use to deduce new geometric facts from those. But this system is still not enough to produce every proof for every geometrical problem. And that is because sometimes we need to introduce some auxiliary elements into the picture. For example, let's see if we have, yes. For example, here we may have, we know something about the triangle, we can deduce things about those facts, but we cannot deduce everything about the triangle unless we add this middle point here. And there's an infinite number of auxiliary constructions that we can do on some fixed figure, while the number of deduction is finite. At a certain point, the symbolic deduction engine will stop, and it's quite early, actually. It's pretty fast. So what we do is we use a language model. So we use a generative model that can work in a space which is basically infinite to suggest us the auxiliary constructions that can be done. And then after we added an auxiliary construction, we again use the deduction engine to make all the possible deductions using this additional construction. And it turns out we can loop this, so we do this over and over, and this is enough to solve a lot of geometric problems. Also there's another fact which is interesting about this system, which is so on the first example, pattern boost, we managed to construct a data set algorithmically. So we didn't need to have thousands and thousands of graphs like scraped online, maybe from some mathematical repository. We could generate them on the fly on our computer. Also, in this example, we can also produce synthetic data in a deterministic way, in an algorithmic way, without having to scrape the web. And we do this by taking some random set of geometric objects. Then we deduce everything that can be deduced using the symbolic engine from those starting assumptions. And then we remove some of the constructions which were in at the start. And then we make now the new problem is, okay, start with the new figure without the auxiliary constructions and obtain one of those facts that's been proven deterministically by the synthetic, by the symbolic engine. And being able to produce data systematically and synthetically is a really important part of artificial intelligence, because it allows us to actually train the model for a long time, which is crucial for having a capable model. Let's now, yes.
Is the model fine-tuned from actual language models, or is it trained from scratch?
So I think in the first alpha geometry paper, I think they used some custom model. I'm not sure if it was already pre-trained. I think that now this is alpha geometry 1. There is a second version, which is alpha geometry 2, which I think uses Gemini. I don't know if it's probably like fine-tuned some way, but I think they leverage Gemini. But on the first iteration on the first like example of alpha geometry, I think they had some custom model. But yeah, I'm not sure if it was pre-trained. Okay, so now on to general mathematics. So we've seen the main specific example, which are maybe one is more limited, the other was a bit more general, but still planar geometry is kind of a limited space. This can be, it's decidable, so it can be solved algorithmically with like infinite time, and mathematics in general is not. So we want some methods that can talk about general mathematics without having to like change our system from a specific problem to other specific problem. And to do this, we need a language that can talk about mathematics as a whole. Okay, so we need a very flexible and general language. And there is, in general, two approaches to this. So the first one is called the informal approach. The informal approach consists in just using plain old, I mean, not so old, but still large language models and just use them to do mathematics without any other maybe modifications. So we can just ask ChatGPT, hey, can you please prove me this theorem? It will try to give us a proof. Maybe it's wrong. It's probably wrong if the proof is non-trivial. If it's easy enough, it can help us get things right. But still, we have no insurance that this proof is correct. We can try to steer maybe the language model to be a bit more knowledgeable about mathematics and a bit more like consistently correct about mathematics by doing some fine-tuning of the model. So, for example, we can start from some LLM which is pre-trained, so it's been trained on the whole internet, for example. We can continue the pre-training on some documents which are math-related. So we can scrape the archive, for example. We can go to Math Stack Exchange and try to make the LLM learn things from there. Then we can try to make it even better at solving problems specifically by crafting some data set that contains step-by-step solutions. So we make it learn that, okay, it needs to start from the hypothesis and make small steps, which maybe it has to reason about until it gets to the conclusion. And maybe it will learn to be a bit better. In the end, we could also provide it some tools, which are, for example, Python, a Python interpreter to do some calculations for it, because LLMs are not very good at like handling large, multiplications with certain, like with 100% of accuracy. So it's better if we let them use an external tools for it. And that's usually it. So we have a language model which kind of knows what it means to prove a theorem, kind of knows what is maybe the state of mathematics if it's been trained on the archive enough, and kind of knows how to use tools. But all of those things, we will never have the assurance that it can do them consistently without hallucinating and without just making stuff up. Now, they're getting better, but still, if you make any language model help you maybe on your mathematical research, you will find it hard to make them do like real trustworthy work. Also, this approach has two main problems, which is the data scarcity. Because, okay, we have mathematics online, we have the archive, we have stuff, but most mathematics that is online is at most undergraduate level. So if you wanted to do research mathematics, hard mathematics is only in hard mathematical papers, which are not, there's not so many. At least if you want to focus on a specific domain, you're not going to find 2,000 papers about these specific problems. So you still need to hope that the AI can somehow generalize and exhibit some capabilities even with limited data, which is not always the case. It's not always possible. But the most important thing is we cannot verify what it says. So we can train it to repeat the things it reads online, but we cannot train it to solve problems because we cannot train it to, we cannot check that it solved actually the problem. So we can either rely on manual checks, so people who check that the AI is correct, which is completely unfeasible on the scale of training, or we can really restrict the domain that we wanted to prove things about to problems which have verifiable responses, which are mainly problems which have a very specific numeric answer. Now, there's data sets that try to do this. For example, there's the data set from Epoch AI, which is called Frontier Math, that has a lot of very hard mathematical problems which have a specific numeric answer, so an answer which is an integer. So you can actually make your LLM try to solve that problem and then check if it's correct. But this approach has two problems. The first, as I said, it's kind of limited. Not every mathematical problem has a specific numeric answer. Actually, probably not. Most mathematical problems do not have like just a numeric answer. And the other problem is, well, what if the AI just guessed the final number? Because maybe the AI got really good at guessing what the number should be. So it tricks us into thinking, oh, it can actually solve the problem. But underneath, it didn't learn how to solve the problem. And so it will not be able to generalize in some unseen domains these capabilities. So to solve mostly the lack of verifiability problem, what we can do is to change our approach and resort, instead of using natural language, which of course is very flexible and can talk about mathematics, like about any kind of mathematics, we can use another language, which is a formal language. And using the formal approach, we can still talk about basically everything that's mathematical, because as we've seen in the past lectures, we can use Lean to talk about basically anything that we can talk about in ZFC, for example. So in the standard mathematical theories. But now we have the advantage that our responses, I mean, the LLM responses are actually verifiable. We can use Lean to automatically check whether there was a bug in the proof, so whether the AI made a mistake. Now, of course, this approach still suffers from data scarcity, maybe even more than the informal approach, because in the informal approach, at least we have the archive, we have mathematical textbooks. In the formal one, we just have Mathlib and a few more examples. So it's harder now to get data, but now we can actually verify what we did. Now, the two approaches are not completely like mutually exclusive. We can actually use them in the same system, and we can envision systems in the future that reason informally, maybe even about something that's not mathematical, maybe about some physical problem, engineering problem, or just everyday problem-solving tasks, but can interleave between the informal reasoning. It can verify some steps. Maybe it says, okay, this bridge, I like this shape for the bridge, but now let's check if the bridge will actually hold. Let's do some calculations, which can be formally verified by an automatic theorem. Okay, for formal theorem proving, so now we focus on the second approach. And how can we do formal theorem proving? Well, there's mainly two ways that we can prompt some large language model. Okay, first start from the fact that we want to leverage the large language models, because they're basically the most powerful tool, the most promising tool in this direction that we have, at least for now. So we want to try and use their power to solve a problem. And we can do it basically two ways. So we can prompt the LLM to do proof step generation. So we give the proof, which is not finished, and we just prompt the LLM, please provide me with the next step of the formal proof. So it just has to write a single line of code. And of course, we can do this recursively. So we can do this from start, from just the statement, up until the theorem is completely proven. Please. And this method can be paired with some tree search, for example, methods to parallelize the search, because we can prompt different instances of the same language model to provide different answers for the next step, and then branch. Basically, we're creating a tree of possible proofs. Maybe some branches of this tree will be more promising than the others, and we can focus more on those. So in this way, we can leverage even parallelization in computing power to solve the problem. Also, in this case, the language model can actually be prompted each time it has produced a new step, and each time prompted, we can put in additional information, which is, for example, the information that comes back from the interactive theorem prover. So we've seen that the interactive theorem prover gives us both errors if you've made a mistake, but also useful information about the context of the proof, of the specific step of the proof. So it can be useful to give it back to the model. This way of doing things can be expensive, though, because we have to make maybe a very large tree. We have to make many branches, and also we need to prompt the model each time. So it can be quite costly and time-consuming. So another way of doing things is to use the whole proof generation approach, which basically means we're trying to make the model solve all the proof at once in one go without stopping. So we just say, okay, please prove this theorem for me, provide a full proof, and the model will try to do it. Of course, we could, we can try to help it by making it make comments, for example, about the proof, so that it can actually kind of stop in the middle of the proof to think in some sense, because the LLMs basically think when they have some space for producing tokens, like in the reasoning models, for example, and we can exhibit some similar behavior inside the proofs. But it cannot use the feedback from the interactive theorem, because producing everything in one go means that we cannot put back the context or potential errors. So maybe the model will make some mistake at the start and it just spends a lot of time to continue the proof, but everything after that point is just rubbish. It cannot be used because there's a mistake very early on in the proof. But it's a more computationally efficient way because we can just prompt it once. It will produce everything at once without having to go in an expensive cycle. Okay, so let's see some useful techniques for both methods. So we start from the proof step generation method. And one technique that's widely used in proof step generation is Monte Carlo tree search. Now, Monte Carlo tree search is an algorithm that's widely used in artificial intelligence in general. It's been used, for example, by AlphaGo, the model still from DeepMind, to beat the world champion in Go. And basically, it is basically a way of exploring the tree. We said earlier that when we make a proof step by step, we're basically building a tree where if we have the possibility of branching, so of choosing two different steps at the same point and see how it goes from those different steps. So what we need is basically a way of exploring this tree. Now there is an ideal tree, which is the tree of all possible proofs for a theorem, for a statement, that is huge. Okay, this explodes very, very rapidly because at each step we can basically do an infinite number of things in mathematics, because we can either use one of the countless theorems we've already proven before, but we can also define any variable which can be any arbitrary real number. For example, we can introduce some combination of real numbers or some combination of objects which we already have. So the search space for each step is basically infinite. So it's not possible to explore this tree in an exhaustive way. For example, we cannot use depth first search or breadth first search, which are the two most basic tree search algorithm in computer science. But we have to choose which branches of the tree we're going to explore. And Monte Carlo tree search is a way of choosing those branches by leveraging some information that we can get from the branches, and also by leveraging a randomness. So let's see how it goes. We're basically building a subtree of this infinite ideal tree. And at the same time, we're going to maintain some function, which is a value function that tells us how good each node that we found till a certain point is, at least from our point of view during the search. So we're going to have some nodes which are more promising and some nodes which are less promising. And so we're probably going to focus on the promising ones. And the algorithm is usually divided into 4 steps. First, which are executed many times. So in a loop, we do these 4 steps. First, we do the selection part. So we start from the root and we explore the subtree that we've already built. So this partial subtree, and we select one of the nodes from this subtree using what's usually called the tree policy. Then we can expand the node that we've landed upon. So from that node, maybe we tell the large language model, please provide another option for proof step from this point. Then we can simulate, and this step is usually done in Monte Carlo tree search. As far as I know, when Monte Carlo tree search is used for theorem proving, this is usually skipped. But this basically is a way of trying to see how good the specific node is by simulating a path. So we simulate a path, so a potential continuation of the proof, and we see how it goes. If it goes well, we give it a high value. If it doesn't go well, we give a low value. But in theorem proving, it's not really easy to say how well a proof has gone, and unless the proof actually finishes the specific goal. Then we backpropagate. So after we did the simulation, or in theorem proving, we somehow evaluated the goodness of a node in some other way, we can backpropagate this to the previous nodes, because the value of a node, which is internal, will depend on the value of its children. So if a node has good children, it will be a good node. And then we go on like this. The selection step will take into considerations how good these nodes are, and it will prefer to go into better looking nodes, more promising nodes. And that's basically just how the algorithm goes. We select a node, we expand this node, then we stimulate some path from this node, and we backpropagate the value to update our belief in the goodness of the nodes. Okay. Now, one thing that has been done using basically Monte Carlo tree search for theorem proving specifically is what is called hypertree proof search, which is basically a generalization of Monte Carlo tree search. And a hypertree in general is a generalization of a tree where some edge can point not only to a single node, but to a group of nodes. So I have one single edge that ends up in a group of different nodes. Why do we like hypertrees to represent proofs in mathematics, specifically in formal mathematics? Because as you may have seen in Lean, if you were the tutorial, there are some cases where from a single proof, multiple proofs, multiple goals can be spawned. For example, if I'm trying to apply some theorem which has more than one hypothesis, then we need to prove each separate hypothesis, and they are basically all separate goals, so separate branches of the tree. And it's convenient to put them in the same group because basically the path that brought to all those proofs is maybe a single application of a lemma. So we like it to be a single edge instead of multiple edges. So we can perform some kind of random search leveraging Monte Carlo tree search also on hypertrees. Basically, in this specific implementation, which is from a paper from I think 2 or 3 years ago, as I said, the simulation step is usually not done. In this case, what they use is a critic model, so a separate model that has the task of evaluating how good each node is, so how good each position is in the tree, and we use that to transverse the tree and to choose which branches are the best. And this is again an illustration of this method. We start from the root. We have groups of nodes, and each new node can point to another group of nodes. We can expand the nodes. So here we can select one group of nodes. We can expand the node. And then we have some way of evaluating how good the nodes are. And again, we backpropagate this value that's suggested by the critic model. Let's now see instead an example of a whole proof generation model. Now this is Kimia Prover, and it's achieved state-of-the-art just a couple of months ago, using a whole proof generation method, using some LLM, so to generate basically everything in one go. But so generating everything in one go, we've seen that it can be a bit brittle because it's not easy to get everything right. Because remember, you don't only have to get the mathematics right, you also need to get the Lean syntax right for everything to compile. So what they do is they try to make the model think very hard about the proof before trying to start before starting the generation. And how to do this is basically in the same way that reasoning model works. If you've tried the new reasoning models, for example, OpenAI 01 or 03, or DeepSeek R1, which are the models that think before giving you the answer. And what they do is usually they put some special tokens, which are called think tokens. And the model knows that after the think token and before this closing think token, it can say everything it wants to try to be in a better position when it needs to actually generate the whole proof. During this thinking phase, this reasoning phase, the model in this case is encouraged to generate actual code snippets. So it generates pieces of Lean code. And the whole pipeline looks like this. So we have as input, we give it the problem that we want to solve, both in natural language and formalized. So we have the statement. And then Timmy Approver will try to reason. It will do many reasoning blocks, which are composed of some important reasoning and some code snippet aiming for. And then just at the end, it will output the whole formal proof by trying to piece together those code snippets in some way. It's also encouraged to actually use those code snippets, because if you just train the model to do this, it may happen that it just says random stuff during the thinking phase, maybe tries some random thing that then is not useful for the actual code generation. So they saw that it's useful to encourage it to actually use those snippets inside the proof, so it doesn't try to improvise the proof when it has to write it. And the training of this model is done in part using reinforcement learning, which we'll talk a little bit more about later. But for those who already saw the machine learning course, they should know more or less what we're talking about. But now you don't have to understand the whole this whole diagram. But basically, here we have a prover, and here we have lean, and the prover tries to solve the problem somehow. We have some checking that, for example, I think this throws away some proofs which are not written in the right format, in the right like external form. And then the lean server checks the proofs which are correct, and the correct proofs are used to train the model to become better and better. So it can basically play with itself with the help of lean to get better at proving stuff. Okay, now we're going to see, maybe now we're going to have a little break for like 15 minutes, and then we're going to see other examples. Okay. Okay, so we can start again. Let me go back a little bit, because I didn't mention one detail, but maybe it's still interesting to mention it. During the Monte Carlo research, I wrote here that the selection step, I wrote that it's usually done using this UCB, which is upper confidence bound method. I didn't explain it though, so let me just say a few words about it because it may be interesting. And basically, the problem here with selection is that we have to balance between exploration and exploitation, which is a general problem in like reinforcement learning and artificial intelligence, trying to balance between exploring all the possible paths that I can take, but also exploiting the paths that I consider the best at certain points. So there will be maybe a first phase where I need to explore more, and then a later phase when I already explored a lot of the possibilities. I need to put everything maybe on a few very promising possibilities. One of the ways to do so is using the upper confidence band. So instead of considering the value of each node, so basically the policy can be, okay, at each step, I see the children of my node and I select the one with the highest value. But this would just make me go a lot of times on the same branches. And maybe those branches were just lucky at the start because they got high value at the start. But remember, at the start, I have very few information. So I cannot evaluate very much how good nodes actually are. So what I can do is I build a confidence bound around the value of the node. And the confidence bound will be based basically on how many times I visit that node. So if I visit the node a lot of times, I will be more confident about the value. So the confidence bound will be smaller. And if I just visited it once, I will have a very large confidence bound because I'm not confident in my evaluation that I gave. And what I do is, instead of taking the value, I take the upper bound, the upper confidence bound. So I try to encourage the model to visit more the nodes that it has visited just a few times. But still, if a node resists this test, so if a node still turns out to be valuable, to be a good node, I will, in the long term, I will still insist on those. Okay. Yes. Now, we've seen examples of both proof step generation, but also whole proof generation. But these are actually not things that are completely exclusive one another. We can find methods which somehow combine both of them. One of those methods is called the truncate and resume method, and was employed by the DeepSeek prover v1.5. Now, DeepSeek prover is a model from DeepSeek, which are the same people who did DeepSeek v3 and DeepSeek R1, which were the large language models released a few months ago, which made the headlines. And this is a specific model for theorem proving in Lean, actually. So this not all the models that we've seen use Lean specifically. Some of them do. In particular, truncate and resume does. Also, K-mean prover used Lean, Lean 4 specifically. And so these techniques try to take something from the Monte Carlo tree search and something from the whole proof generation. So it tries to be both like powerful and explore many things, but also efficient, leveraging the whole proof generation. And what it does is, okay, it would perform a Monte Carlo tree search, so it still build the tree, but the difference between just proof step generation is that instead of producing a single step when it's prompted to do the generation step, so the expansion step we called it before, instead it tries to produce a whole proof, so a whole completion of a proof. So it starts from some node and produces a lot of lines, but then those lines may be faulty, they may have some mistakes, or they may not conclude the proof. And so what we do is we truncate the produced code at the first time it gets an error. So maybe at a certain point, we encounter some syntax error, or maybe we encounter some actual mathematical error, or maybe we just have the error at the end, which says, oh, you didn't complete the proof, you forgot to prove some goals. In that case, we just keep everything. If there's an error, instead we'll discard everything which is after the error. Then with the truncated proof, so that the part of the proof that actually compiled, that worked somehow, what we do is we divide it into multiple steps, because it's just a big chunk of code, but we can still break it into single step tactics. And then all these new steps get added to the tree as new nodes. And we can see that this is a depiction of this algorithm. So we start with some statement and a partial proof of the statement. Then we try to make here we try to see what's the context in this at this specific step. So the model we can leverage information about the context from the ATP. Then it is prompted to do whole proof completion. It produces all this proof, but the proof has an error here, so we just discard this part. We break the working part into multiple nodes, and these multiple nodes here we have the tree that we're building. These nodes can get added to the old tree to make a new tree, a new subtree, which is bigger. And then at the next step, what we do is we can stop not only at the leaves of the tree, but we can also stop at some intermediate nodes. So maybe the proof that is produced is not faulty. I mean, it doesn't get us an error, but proofs, as we've seen during the tutorial, we can actually put tactics there that make the goal unprovable, because maybe we were using a very powerful lemma, which has very strong hypothesis. I mean, that lemma could make us conclude the proof, but maybe the hypotheses are not met, so we need to go through a different path. But with this technique, even if the proof at some point, without giving us errors, makes the goal impossible, we still have a chance to stop at some earlier point and branch again, and so we can still reuse the first part of the proof that maybe was already useful and already made some significant progress.
which tree policy is used. So how do you decide at the next simulation where to stop?
So I think in this case, they use some variation of UCB. They use, I think, discarded UCB is called.
So there is a value function.
I think that they estimated somehow. I don't remember the exact functional that they used to estimate the value. I think I think somewhere in the paper they say that they use some kind of intrinsic reward, but I don't remember the specifics of this. But yes, somehow there is somewhere a notion of how good the nodes are. So some kind of value function is added. I think I think they have some also in the reward they have some way of encouraging the production of new like the exploration. So I think maybe steps which have not so many children are also encouraged. But I don't have the formula right now.
Sorry. So the model automatically knows which are the part of the groups that are good, or
so, yeah, it tries to estimate it. So as I said, I don't remember the exact formula. It doesn't try to. I mean, it's not. I think it doesn't have a critic model in this case. I think the evaluations are done based on how the tree is, and they are done in a way to encourage exploration. But yes, I think it doesn't have an explicit estimate for how good some parts will prove, how good like how likely it is to prove maybe to complete the proof from a certain point on. Whereas, for example, the Monte Carlo, the hypertree proof search, I think they had an explicit model that actually was there just to estimate what was the probability that specific goal was finished. And in that case, since they had like multiple like hyper branches, basically the value of a single node was calculated as the product of the probabilities of its children nodes from a single edge. So because of course if you produce like 4 different goals from proof, and you estimate that you have like 50% of chance to solve the first 2, and then 100% for the other 2 because they're very easy. Then the chance to solve the previous goal, and you need to solve everything, so you have like 25% of chance. But yes, this can be handled in different ways, and it's in general a very hard problem to estimate how good in a position we're in during a mathematical. It's hard to determine how difficult the problem is if I don't know how to solve the problem, or if I don't have or at least a sketch of the proof in my mind.
And this is not a hypertree, right?
No, this is not hypertree. This is basically what. Okay, so we were talking about this just a few minutes ago during the break. Basically, if you're building a simple tree for the search, what you're doing is you're underneath you're linearizing your proof, because in the end the final proof will be just a single path from the root to one single leaf node. So it's a linear sequence of steps. So what you basically do here is you just treat the proof as a single sequence of tactics without considering, for example, if you branch the proof in 2, you just consider them one after the other, the 2 branches. While with hypertree proof search, a single proof, so a path from the root node to, let's say, a leaf, is itself a tree, because we have these, like, let's call them like implicit branching, where you have multiple nodes in a single group with a single edge that point to them.
Do you know it can happen often that you reach the same exact proof state in different ways, or is it very often?
It's no, it's likely, especially if you're so for example, if you're proving something I don't know about measures, it's very likely that you will need to prove measurability, maybe measurability of the same function like 5 times during the same proof, because different lemmas all need the same measurability assumption, or maybe the same unknown non-negativity assumption about some constants. And so, yes, it can happen. And in some works, they treat them basically as a DAG, which is I don't remember what is the acronym for, but it's basically a tree which can, yes, directed acyclic graph. So it's basically a tree where you can have nodes like leaves, for example, that coincide. So it's a tree that can touch itself again without always branching. You can have basically the same node can be in different positions. You can see it also there in that way.
Because in alpha zero, in the color research, you reach the same position in 2 ways, like it's actually collapsed as a
Okay. Yes, maybe even in the hypertrophy proof search, they use some kind of like collapsing of different proof steps, different like situations in different parts of the, like the same situation in different parts of the tree. Okay. Now let's go on and let's see a couple of other techniques that are widely used, that are maybe used in some ways in this field. And one of them is draft-sketch-proof, which is a general framework. This is not a specific model, but it's a general framework for proving, so automatic theorem proving, which can also actually be adapted to autoformalization. And what we do is we basically split the process of proving something into three steps. And this is how it looks. So the first step is called the draft. So we start from the statement of the theorem, which can be either a formal statement or an informal one. And we try to produce a draft of the proof, which is an informal draft. And this can either be done by some large language model, maybe some big informal reasoning model, which can actually do some reasoning, but is not very precise as writing code, for example. Or we can just use a human written proof. If we have the human written proof available, we can just use it, and then it becomes an autoformalization task. Then the second step is a sketch. The sketch is a translation of the informal proof to a skeleton of the formal proof. So we basically take the formal proof. For those of you who've seen the tutorial, we can make a sequence of have statements. So we introduce a sequence of mathematical facts, which is basically what happens in the informal proof. So we do not prove the connection between one fact and the other. We just list them, and of course, we need to formalize them correctly. So we make an autoformalizer model do this, which should be a language model that's capable of writing syntactically correct Lean code at least. Maybe it can be not super strong in reasoning, but it should be a good coder. And the final step, which is the proof step. Now, in the original paper, they use some out-of-the-box automatic theorem prover. In particular, the original paper was not implemented in Lean. It was implemented in Isabelle, which is another formal language which was mentioned in the first lecture. Isabelle has a logic underneath that's a little bit less expressive than Lean, but this allows for much more powerful automation. In fact, in Isabelle, we have a tool that's called Sledgehammer, which is basically an automatic theorem prover that tries a lot of things. It tries to apply some SMT solver, for example, satisfiability modulo theory solvers, or other automated external solvers to solve a problem basically by brute forcing it logically, and then translates the result, the certificate back into the Isabelle language. And I believe we do not have a hammer at the moment that's as powerful as Sledgehammer. Some tools are emerging. There is some new tools just in the last few weeks that may be promising, may develop into something that looks more like a hammer. There is grind, which is a tactic that's being developed right now by the Lean FRO, which may be some kind of hammer, so something that you can just throw at your problem, and it tries a lot of things. It tries to brute force the problem, and for reasonably like short problems, it should basically succeed most times. And so basically, what the only step where the theorem prover actually needs to write lean code is this step in the middle. And the last step can be done very efficiently because automatic theorem provers like Sledgehammer are usually quite fast at solving things. While the first step can be done by a more general model that, again, does not need to be fine-tuned on lean specifically. So it's a framework that can be adapted to a lot of situations. And also we could substitute the last layer basically by another language model that's not just an automatic theorem prover, which is deterministic, but some more generative model. And something like this was also done in the DeepSeek V2 paper, where they basically decompose the proof using a very powerful model, and then they use a smaller model to solve the single the little holes which are left in the proof.
I don't know if we just to the question, but maybe we can do it. But in the draft, we use the language model to generate the normal proof. But why we use the language models, not the other one? Which is the relative.
So the automated theorem prover here is not language model, so it will never be able to do any of those two steps, because this just tries to translate the problem algorithmically in some external solver, like, I don't know, Vampire, for example, or Z3, and then it gets the solution back. So this cannot do any of those tasks. For these two tasks instead, we can use language models for both of those. Now, in the original paper, I think they used the Minerva model for this, and the one that had the best performances was a large model. I think maybe hundreds of billions of parameters. While for this other step, they used a codex model, which is a model that's fine-tuned on producing code. So it's good at code and also at math, and it's much smaller. So this one is good at getting the syntax correct. But this model is much better at reasoning. So this model here maybe cannot actually fill in the gaps in the proof, in the original proof. While this big model can produce a proof that's detailed because it can reason, but maybe it makes mistakes, it hallucinates, or it kind of write in lean. Actually, so this paper is from, I think, 3 years ago now, maybe 4. And now the more recent models can handle both of those tasks. Usually, so even big models do not need like an auxiliary one, an auxiliary model to produce formally correct, like syntactically correct lean code. But yes, this remains in general a framework that can be useful even if you're just using a single model to do both tasks, because it's useful to first like reason informally, because you don't have to care about the lean syntax, and then to translate your reasoning so you can let go of the reasoning part and focus on the calculation part, and then maybe focus on the proving part of the details. Okay, now for the last part, I would like to focus on a specific branch of artificial intelligence, which is called reinforcement learning. We already seen some examples of reinforcement learning before. And reinforcement learning is, in general, one of the like 3 big ways in which AI people train their models. So we have supervised or unsupervised learning, which are the other 2 methods. And in supervised learning, we basically make the model learn from some labeled data. So we have net data, maybe manually, or some cases artificially, like synthetically produced labels or manually produced labels. In unsupervised learning, we try to make the model learn from the data itself. In reinforcement learning, instead, the idea is to try to make the model learn by interacting with some environment. So the model in this case is sometimes called an agent. So it's some entity which can perform actions. And the actions will influence the world around him, and the world around him, so the environment, will respond with a new state. So the model will be in a state from the start. It will perform an action, and it will find itself in a new state. So the environment around it will have changed, and it will receive some kind of reward signal, which tells the model whether it did good or bad. What the model wants to do is to learn a policy, so a way of behaving that makes the reward as big as possible. So the model tries to maximize the reward. All of this is quite vague because there's a lot of different ways in which you can define the reward. It can be a reward which just kicks in at the end, or it can be a reward that's given during the learning. In particular, in theorem proving, we can consider the reward the fact that you finish the proof. And so it's sometimes called a sparse reward, because you just get the reward at the end while you finish a lot of steps. And for any other situation, you get a zero reward. And for this reason, it could also be useful to try and develop some systems to estimate how good a position is, so we can give a reward to the model if it gets into a better position, for example. But as I said, that's a very difficult task to achieve. Now, examples of reinforcement learning. These are examples that we see also during the machine learning course, so you will recognize them. But three very frequent situations to use RL are, well, when you have to train a robot to do something, because you can let the robot act in the environment. Maybe you give it a reward if it completes some tasks, and maybe you can even give negative rewards if it breaks stuff around him or if it falls down. Another environment where it's very frequent to use RL is games. We have a lot of examples of games which are basically solved by RL. So we have the famous example of Go. Even before we have chess that's solved. But now AI can play even more general games like board games or like online video games. And RL is usually the backbone of the training for those kind of agents. And the last example we've seen is language modeling. So we've seen that we can actually use reinforcement learning to get better language models. In fact, the last part, one of the last parts of the post-training of LLMs nowadays is usually done by RLHF, which is a reinforcement learning with human feedback, where the model learns what basically humans like as a response. Right. All these three different fields all have some kind of similarities actually with formally proving or with proving stuff in mathematics, but all in a different way. Because, for example, in the case of robots, I think the best analogy that can be made is that a robot usually has a very, very wide space of actions available, because it can move maybe in a almost continuous amount of ways, in more directions. It can perform different actions. But the robot usually has an environment which is hard to simulate. Instead, in mathematics, just like in games, at least in most deterministic games, we're able to actually simulate the mathematical environment with extreme precision. And in the case of Lean, the simulation is Lean itself. So the environment in which the agent learns and acts is the interactive theorem prover. Lastly, the analogy with language model is actually quite direct, because basically, to do mathematics, we have learned that a good way is to use an LLM to produce text, and this text is just the code, which is Lean code in this case. So theorem proving is kind of similar in some aspect to all those examples, but still it's peculiar. It's not completely like similar to any of those single examples. And that's why we actually can try to use RL, and we can hope that RL actually works for this task as well. Now, we've already seen like a very typical example of reinforcement learning before. Let's see another example, which is maybe more implicit, the fact that it's reinforcement learning. And it's called expert iteration. This is a technique that's used in a lot of recent papers and implementation about theorem proving. It's been seen to work quite well at improving the performance of the final agent. And expert iteration works like this. Basically, you have a self-improving loop where the agent learns to make better proofs while it only has available some statements to prove. So we don't have to provide the agent with already written formal proofs. And that's why it's not supervised learning. That's why we can call it reinforcement learning, because the agent can interact with the unproved statements, try to prove them, and let's see how it can improve itself. This is done into two steps. First, the theorem prover attempts to solve the problem. Maybe you have 1,000 problems. It tries to solve them out of the box. Before this, we may have fine-tuned the model in the ways we've seen before, maybe on some big mathematics corpus, on some problem-solving specific material, and maybe we even gave it some specific lean training to make it able to write, or maybe if we're not writing in lean, some other interactive theorem prover. And then we try to make it prove some theorem. So the model already needs to be able to prove at least something for this to work. But maybe out of the 100 theorems, out of the 1,000 theorems, it's able just to prove 100 theorems, so just one out of 10. And what we do is we take those 100 theorems and we put it back into the model as fine-tuning material. So now the model, with the theorems which are now proven, because we were sure that those theorems are correctly proven because lean tells us that the proofs are correct. So we can confidently feed those proofs into some fine-tuning steps, so some supervised fine-tuning steps. So the model reinforces those actions that led to successful proofs. And then this new model, this new fine-tuned model, we can put it back into the attempting environment where it can try to solve some of the remaining like 900 proofs. It will solve some of them, and again, we can take the solved problems, put them back in the loop, and make the model even better. And we can do this basically until the model manages to prove at least one new proof at each iteration of the loop. Okay, yes, then that's just the description of that I just said. And this is a very simple way of doing reinforcement learning. Because you just need you need not many data, you just need the statements. But it's been seen to improve the performance in many different scenarios, so in many different models. So it's quite widely used. Oh, and also this method basically builds what's called a curriculum of a learning curriculum. And a learning curriculum is some learning data set that is ordered by the faculty. And that's been observed to make for a much better later learning data set, because if we make the model first learn easy things, so it can pick up some skills, some initial skills, and then we feed it more and more complicated stuff, it will learn much more efficiently than if we just throw random stuff at it. And that's actually just like humans also learn, because we cannot just throw a super hard university problem at a 7-year-old child and expect him to learn something from it. On the other hand, if we make it, if we make the child prove easy problems that are manageable for him and increase the difficulty with time, you can expect him to become better and better. And in this case, we don't need to like manually grade the difficulty of the statements, because it just emerges, because the easier statements will be the ones that actually get proven at the start.
The first example that you gave today comes into
oh yeah, pattern boost.
Is it like itself also a kind of expert iteration?
I mean, I guess it can be seen somehow that way. I think expert iteration is a term that comes to more general problems. I don't know the exact environment from which it was first applied to, but I think it was a little bit different from from what we do in theorem proving, which is basically just use a single model. I think in general, expert iteration involves more than one model, because I think you have some expert model that, I don't know, interacts in some way with some weaker model to make it learn. But in this case, basically the expert model is the model itself, because it becomes better after each learning loop. But I mean, it can be seen as, I guess, kind of some reinforcement learning strategy, pattern rules, because you basically have the environment, which is the score function, which is a super simple environment that just tells you, okay, this graph that you produced is good. And then what you do is very similar to expert iteration, because you just train the model on the good graphs that you've already produced. So yes, in some ways it's kind of similar. Okay, now this is the last example that I will be doing today. And this is one of the last, like one of the most powerful models probably in existence today, and it's called AlphaProof. It's again a model from DeepMind, which we've mentioned already, I guess, at least 2 times today. They're quite present in the field. And AlphaProof is a general theorem proving model that writes in Lean. So this is a Lean specific model. And uses LLMs internally to solve problems. Specifically, it's been used to solve international mathematical Olympiads problems. In fact, it was used on the last Olympiad last year in 2024, where it managed to score 28 out of 42, which is the upper boundary actually of the performance of the silver medalist that year. So with just 1 point more, they could have claimed the gold medal, but unfortunately for them, they didn't manage to do it. And it was mainly in this case because of combinatorics problems, because you may know that in the IMO, there's 4 different categories of problems. And it turns out that the combinatorics problems are particularly hard to formalize in Lean. So there were 2 combinatorics problems in that year, and they were 2 problems that the model didn't manage to prove, while the 4 other problems were completely solved either by AlphaProof itself, or in the case of the geometry problem, it was actually solved by alpha geometry in just a couple of seconds, while AlphaProof took almost 3 days to complete the other three problems. And why I'm mentioning it after RL is because they actually use RL internally in a very interesting way. Now, we do not know everything about AlphaProof because it's not public. So as far as I know, we don't know many details about what model it is and exactly how they make it learn. But one thing they share is how they use what's called test time reinforcement learning. Now, test time reinforcement learning goes like this. So you're not trying to train your model. So not before you're like participating in competition, for example. You're not doing this as a previous step, but you're doing this during the duration of your proof. So you start attempting to prove some kind of theorem, and while you attempt to prove this theorem, you try to improve your model at the same time. And what you do is you try to make different variations of the original problem. So let's say we start from some hard algebra IMO problem. They will prompt some language model that in this case I think is Gemini, to make many variations of the problem. And then we get AlphaProof to try and solve all those problems. And maybe they get lucky, and some of the proposals of Gemini, of the variation proposals, are actually easier than the original problem. And maybe the model, if it's capable enough, it manages to prove at least some of them. So after we've proven some of them, we do a thing that's very much similar to what we do during expert iteration. So we basically we fine-tune the model on the correct proofs that it produced. But in this case, they're proofs which we hope are very similar in flavor, let's say, to the expected proof for the final problem, because maybe they will handle the same kind of objects. It will need the same kind of intermediate lemmas. And so what we hope happens is we start with a very hard problem, and we start with a model that's capable of proving things, but just these things here. So it's capable of proving things which are far from the hard problem that we want to solve. Then we try to produce a lot of different variations of the original problem. These are all produced automatically and are also formalized automatically. While the first, so the first problem here, at least the approach that they had last year was they didn't formalize the problem automatically, but they had some lean experts formalizing the statements because they wanted to be really sure that the statement was like correct and it did not hallucinate on that. And in fact, this was a huge setback because one of the two combinatorics problems, even the lean expert didn't manage to prove it in time, to formalize the statement in time. So they didn't manage to even start search with the model because it was too hard to write down in lean. Because in general, combinatorics problems need some kind of auxiliary, maybe a typical structure, because maybe they describe some kind of game. So you actually have to formalize all the game structure, which can be really non-trivial. So they produce all these variations, and you see the model maybe touches just one of the just one bit of the possible variations. But if it manages to prove at least some, they can fine-tune it on the correct proofs, and so the model will be able to prove some more things in this domain, and then we can do it iteratively until the model is capable enough and is fine-tuned enough on this specific domain that it manages to prove the original problem, and then we're done. So of course, this is an extremely costly technique. It's extremely expensive from the point of view of the computation it has to do, because for a single problem, you need to not only solve probably thousands of, or at least attempt to solve thousands of variations, you have to produce the variations first, and you have to fine-tune the model, and then this specific model will not be able to solve any problem. It will just be very good at this specific model, so you have to do it again from scratch. If you change a problem, at least if you've done it just a limited amount of times, you cannot hope that it will generalize a lot, because all the variations again are very similar to the first problem. But still, it's a way to solve problems which may be extremely hard. I mean, arbitrarily hard, and it also is very much similar to what we do as mathematicians. Because if we're tackling a hard problem, we will try to do variation. We try to solve to make partial solutions to problems, to solve easier problems first, to understand the field we're in. So I think it mimics a lot how a mathematician tackles a problem, and so it may be applied to problems which are many orders of magnitude harder than just unlimited problems, which may take a couple of hours, maybe to some expert students to solve. Maybe you can do it over the course of months with, of course, a lot of compute, but to solve problems like Millennium Prize problems, for example. Okay, so that was the last example I want to give. Here's some bibliography that I use for to make the presentation. So if you're interested, I will upload the presentation on Virtuale for the students that are interested. If you're interested in the presentation and you're not on Virtuale, just tell me, I will give you, of course, everything. And yes, in general, thank you everyone for having followed the lectures. I think this is a very exciting field to be in, and I hope more people will come join us, both in the formalization side and in the AI for math and AI for formalization side, because I think they are very promising paths, and we're likely to see like a change in the way we do mathematics thanks to these new tools. And yeah, I think they will shape actually the future of our field. So as many people, the more people will contribute to them, the better it will be, I think. Thank you.
Grazie mille Lorenzo, ciao.
Grazie a te, grazie di esserci stato. Ciao ciao. Ok, registrazione.